If you have ever scraped the surface of mathematics, you have almost certainly heard of one particularly notable mathematician, Carl Friedrich Gauss. Perhaps you have studied the normal curve, often called a Gaussian, in statistics and probability. Perhaps you encountered Gaussian elimination in linear algebra. In numerical analysis, Gauss seems to be everywhere. So, when such a prolific mathematician calls a theorem remarkable, it has to be good. This is the Theorema Egregium, Gauss's remarkable theorem. The theorem is rather simple, of course, once we parse through what these mysterious terms are: Gaussian curvature and local isometries. There are some technicalities for rigorously defining what a surface is, but for the sake of this video, when I tell you that a plane and a sphere are examples of surfaces, I think you get the idea. I do want to explain what this theorem means, but it is not the main point of the video. What I really want to explain is not a proof, but a point of view that has become essential in modern physics and differential geometry: the intrinsic point of view. Many of you may have encountered this point of view in Edwin Abbott's classic text, Flatland. This book follows a two-dimensional world in which the main character is a square, just doing flatland things. Given our three-dimensional familiarity, I expect that most readers will find themselves looking down on flatland from a higher plane of existence, like we are. This is the extrinsic point of view, the view of how one space is embedded in another space. On the other hand, the flatlander, at least initially, is oblivious to the fact that they might be embedded in anything. They just see the 2D world they live in from the 2D perspective. That is the intrinsic point of view. In the Theorema Egregium, Gauss identifies one of these intrinsic properties: Gaussian curvature. Initially, the curvature of a surface seems to be something you observe extrinsically. It has to do with the surface bending in some space. This gives some motivation for why curvature's intrinsic nature is so surprising. Look at our flatlander. In fact, let's start calling it a surface lander, which is still a square from the intrinsic point of view. I claim that such a surface lander will know that it lives on a curved surface despite lacking the extrinsic perspective. It will take some work to understand Gaussian curvature, but I claim that understanding its intrinsic nature can change the way you view the universe. We start at a very intuitive place by asking, how much does a curve curve? Simple enough, right? Clearly this curves more than this, but how can we quantify this? As it turns out, there are a few equivalent ways to characterize curvature, but there is a geometric answer I particularly like. We will use a new object called an oscillating circle. This is our curve, a parabola. We will try to find how much it curves at x equals 0. Let's draw a small circle at this point facing the direction of curvature. Now let's keep increasing the radius of this circle until it just kisses the curve. Once we have this circle, we take the reciprocal of its radius, and this is the curvature. Look what happens as we narrow the parabola. Now look what happens as we widen it. If we keep widening the parabola to a line, the circle will, in some sense, approach a radius of infinity, implying zero curvature. This makes sense. A line does not curve. To make precise the notion of kissing, we can use the fact that a circle is uniquely determined by 3 points. Let one of these points be a point where we want to find the curvature. Then, look at the limit as the other 2 points approach. This circle is the oscillating circle. In this sense, this circle best approximates the curve near the point. Now that we have a notion of curvature for curves, we can bump up a dimension to surfaces. As with curves, there are a wide variety of possible ways to approach the curvature of surfaces. Some are far more technical than others. I want to give a nice geometric picture while keeping technicalities to a minimum. Then, we will be quite close to the Gaussian curvature half of the Theorema Egregium. To make progress, I will define something called normal curvature. Here is a surface called a hyperbolic paraboloid, often called a saddle. If it looks familiar, it may be because this is the shape of a Pringle. We have a curve on a surface C. Let's find the normal curvature of this curve at a point P. Let's also show a normal vector to P, that is, a vector pointing in a direction perpendicular to the surface. Note that there are 2 possible directions for such a vector. The normal curvature at a point on the curve measures the curve's curvature in the normal direction. Let's find the normal curvature of this curve C at this point P. Notice that C curves entirely in the normal direction, so the normal curvature reduces to the pure curvature of C. Thus, we can play the oscillating circle game to find its curvature. Now, let's look at another food-resembling surface, a torus, which is the shape of a donut. What is the normal curvature of this curve C at point P? From an extrinsic perspective, the curve looks like a circle, which has curvature 1 over the radius. However, notice that C does not curve at all in the normal direction. Therefore, it has a normal curvature of 0. If we take the flatland point of view, where we live as two-dimensional beings on a donut world, traveling along this curve is no different than if we traveled along a circle in a plane. This gives some intuition for why 0 normal curvature makes sense. I fear treading too deep into abstraction, but now is the time to drop the punchline. Consider all the infinitely many curves passing through a point on a surface. Take the two with the maximum and minimum normal curvatures. These curvatures are called the principal curvatures. Their product is the Gaussian curvature. It may seem at first like an arbitrary measure of curvature, but the concept of Gaussian curvature is essential, mainly for its role in the Theorema Egregium. However, just leaving that behind at the moment, I want to give an intuition for why it makes sense as a measure of curvature. To add some notation, kappa 1 and kappa 2 are principal curvatures. Geometrically, 4 things can happen based on the signs of the principal curvatures. If both are positive or both negative, we have an elliptic point. For example, all the points on a sphere are elliptic points. If the principal curvatures have opposite signs, we have a hyperbolic point. For example, the point shown earlier on the hyperbolic paraboloid is a quintessential example of a hyperbolic point. If one of the principal curvatures is 0, we have a parabolic point. The points on a cylinder are perfect examples of this. Finally, if both principal curvatures are 0, then space is flat, a plane, as it is in flatland. And voila, half the theorem makes sense. If this felt daunting, the other half about local isometries is far easier. What is a local isometry? Here, a bit of Greek will go a long way. Isos translates to equal, while metron means measure. So, a local isometry in this context is a transformation between two surfaces that preserves the length of any curve. To give a classic example, this plane and this cylinder are locally isometric. Watch how the plane can wrap into the cylinder while preserving the distance of the curve. We can now understand the Theorema Egregium. To drive things home, an example is called for. We already established that a plane and cylinder are locally isometric. By the Theorema Egregium, they should also have the same Gaussian curvature, and they do. It is 0 in both cases because of the flat direction. Another more concrete example has to do with maps. You have likely heard that it is impossible for a flat map of the Earth to faithfully represent distances. In our new terminology, we would say this fact is equivalent to a plane and a sphere not being locally isometric. If they were, then they would have the same Gaussian curvature, but they do not. The points on a sphere are elliptic, whereas the points on a plane are flat. Hence, all flat maps distort distances. Nowhere do the words intrinsic and extrinsic appear in the Theorema Egregium, but the theorem has everything to do with our surface lander, in this case, flatlander. I said I would not be explaining the full proof of the Theorema Egregium, largely because of the number of technicalities involved. However, one way to go about this proof is to show that Gaussian curvature can be found just by measuring lengths and angles on the surface. So, our very smart flatlander square would be able to tell that they live on a surface locally isometric to a plane. In a formal setting, you can derive some messy formula like this to show that Gaussian curvature can be found by measuring lengths and angles on a surface. To give another nice example, we know that the sum of angles on a triangle in flat space add up to 180 degrees. However, a surface lander on a sphere would draw a triangle and realize that the angles add up to something larger than 180 degrees. This indicates to them that their world cannot be flat. In terms of the definition I gave earlier, that Gaussian curvature is the product of principal curvatures, it should be shocking that curvature is intrinsic. The principal curvatures themselves are certainly not intrinsic. Amazingly, their product is. What initially seemed extrinsic is intrinsic all along. Earlier, I made the rather audacious claim that the intrinsic point of view can change the way you view the universe. To this point, I want to end with a nice connection to Einstein's theory of general relativity. If you are not familiar with this theory, it is the most modern understanding of gravity. I will make no attempt to explain relativity in depth, but physicist John Wheeler famously summed up this theory concisely, saying, "Space-time tells matter how to move, Matter tells spacetime how to curve. In comparison to the two-dimensional surfaces we have been studying, spacetime is four-dimensional, with 3 for space and 1 for time. Understanding curvature for these high-dimensional objects, known as manifolds, requires a lot more sophisticated machinery, much of which was introduced by Gauss's student Riemann. However, it is fair to say that the generalization of Gaussian curvature for surfaces is the Riemann curvature tensor for these higher dimensional objects. In the context of general relativity, this tensor contains the curvature information for spacetime. Have you guessed by now? The Riemann curvature tensor is intrinsic. For general relativity to be a well-tested theory, it has to be. We live in spacetime. To get any measurements that we can test, we have to be able to gain knowledge about the curvature of spacetime from the perspective of spacetime. In this way, we are just like surface flatlanders. We know how much our reality curves just by living in it. In general relativity, we never have to care about spacetime's embedding in anything. We can still fully understand the theory all from the intrinsic point of view. And who knows, just as the flatlander square eventually found that there is a higher 3D space beyond their plane, we may find that there are higher dimensions beyond our spacetime.